double check if we're live or not. And during that duration, I'm always freaking out because I find out new ways of messing up.
Yeah, no worries.
Just one moment. I can hear an echo, which means things are good, thankfully. Awesome. I'll quickly introduce Daniel and what he'll be talking about and hand it over to him. Let me mute the other tab so you all don't hear that. Hey, everybody. Thanks for joining us again on a Sunday. Super excited to bring back the Jack Stocks. Today, we're joined by Daniel Freeman, who's a senior software engineer at Google Research. He spends most of his time trying to do cool things with reinforcement learning, and before the call he was telling me he wouldn't be doing this stuff if it was as fun to him as it is. uh, Prior to Google, he got his PhD at UC Berkeley in physics, studying quantum information theory, and he'll be talking about the Brax framework, which also is a physics engine. It's a new differentiable physics engine built on top of JAX, and he'll be showing us an interactive demo, accelerating training on accelerators. That's quite a mouthful. So I'm excited. Last time we destroyed a sandcastle. Let's see what Daniel teaches us this time. Thanks for joining us, Daniel.
Awesome. Thanks so much. Yeah, so this is Brax. Here's some environments in Brax. They actually have even more than this now. This is just a slice of the fun stuff happening in Brax. This first link here has a bunch of neat interactive collabs that one can run in one's browser if one so wishes. Today, I actually wanted to show off our training collab because it's pretty slick. So let me do some rapid fire tab switching here. All right, can you see this tab okay?
I can see training in Brax.
Great. All right, so this is training Brax. So I'm using a free public Collab runtime, so anyone can start one of these if they just navigate to that link that I was showing that you can't see now. But make sure you don't forget to attach a TPU by going to change runtime. Make sure your runtime is a TPU. It also has instructions right here. So let me kick off a few cells really quick. Let run while I talk. All right, so these are launched. I'm going to go back up to the top. Alrighty. So this collab showcases how we can use Brax to train policies really fast from a browser. We have this in Collab JavaScript-based rendering that's powering this ant visualization here. Makes it easy to prototype a new Brax system or just visualize your policies of these little creatures actually doing things, which we'll see in a moment. These notebooks have some drop-down menus that actually let you visualize a couple of different systems in our release. Because it's doing something in another slide, or doing something in another cell, I can't switch between these quickly. But we have a handful of different environments here. There's the Mujoko likes, which are like ant and humanoid and half cheetah and reacher. We also have like Walker 2D and swimmer and other stuff, which just aren't updated yet on this slide. As well as our dexterous manipulation environment called Grasp, and then a goal-directed locomotion task called Fetch, and finally a kind of 3D reacher-like task using a UR5E arm called UR5E. Under the hood, these system definitions are really simple protobuf specifications of how rigid bodies are connected to each other. So that's like how these joints are connected, how they're actuated, which things are allowed to collide, reminiscent of Mujoko XML or just like URDF files. We actually have some support for conversion of Mujoko and URDF files into Brax, but it usually requires a little bit of extra massaging because of some fundamental engine differences. We're actually working on making this less painful right now with an upcoming upgrade to the internals of Brax, which I might talk about a little bit later. So
I'm sorry, I have a new question. The
Yeah,
Mujoko file formats and the other ones you mentioned, these are, I believe, environment files that are standard in the world of RL. Okay.
Yep. Yeah,
Thanks for
exactly. So you can explore the structure of like how we define these things in our one of our other collabs called Basics, which is that previous link. So these protobuf files are really just like half of the RL environment. The other half are usual gem-like methods, things for observing the world, defining a reward, defining how the system steps that we all expect from our favorite wrappers around Markov decision processes. And these are all defined in the Python system files in our repo in Jaxy Python. So, and they're also written so as to leverage Jax's compilation and vectorization primitives. So while I've been talking, our ant environment has been initialized, has been evaluating in 2048 environments in parallel. and it's generated experience for our custom implementation of PPO. And because the env and PPO compile alongside each other on the same TPU, everything goes blazingly fast. In fact, while I was talking, this ant already experienced 50 million frames of experience. So it learned to walk. And let's keep going down here. And like I mentioned a minute ago, we can visualize this policy. So here's our ant running. Cell, it's generating a little trajectory for our ant. And I'll give it a couple more seconds. So the output of this whole training process is really just a flax neural network. So it's just like NumPy weights that you can kind of immediately have in your hands and do whatever you want with. So it's pretty straightforward to just take it and do whatever. So here's our little ant running furiously rightwards in pursuit of ever greater rewards. I'm just gonna look at our ant here, looking to run. All right, so that concludes the live demo. Happy to answer any questions about this, talk more about training things, if there are anything.
No questions so far. I'm just fascinated and staring at the ant.
Yeah, I mean, it is sort of mesmerizing. Like really my day job is just training a lot of these creatures and like watching them move when testing different physics things. So it's fun. Maybe I can launch like a humanoid while I'm talking. We'll look at that in a bit because humanoid's fun to watch.
For the audience, I wanted to mention Christian unfortunately isn't able to make it today. He'll be hanging out in the YouTube chat if anyone wants to talk to him.
I'm going to fire this off and then maybe we can look at this after I finish the rest of my talk. All right, so let's hop back over to the talk portion. And again, so this GitHub link is where a bunch of other notebooks are as well, like our basics collab, multi-agent collab, just all collabs that can be interacted with if you just take kind of the GitHub part of the URL and go to just a collab window with them. So this is like how you load this collab. There used to be a slick button that you could press, but then GitHub like broke the way those links worked, so it's not quite as easy as it used to be. Anyway, so I like this figure because it's sort of an abridged version of Brax's life story in one slide. Early in our project, we started training locomotion policies on beefy CPU cloud machines, and would usually kick off these locomotion policy training runs to run overnight so that we could look at them in the morning, and this would take hours to train. And then we spent a good chunk of time spinning up distributed reinforcement learning infrastructure to get training time down to minutes, because it's, you just need more experience more quickly and you can do it. But this required running thousands of simultaneous CPU jobs to be able to generate experience fast enough. And finally, because that's kind of completely insane to expend that much resource to generate a locomotion policy, we built this minimal rigid body physics engine that could compress all of those computations happening across that cluster down to just one accelerator. And it's not quite as insane as it looked. Like this picture in the middle here, like each one of these CPUs was like running one copy of Ant, more or less. So there's just a ton of room to actually accelerate this process when you vectorize over things, when you don't have to deal with network latency for sending data, across the wire to some central server. This was an easy opportunity, I would say. All right. So here's a kind of a landscape of other differentiable engines. We were not, of course, the first people to put together a differentiable physics engine. So probably the two closest engines in terms of feature coverage and implementations are difftaichi and Tiny Differentiable Simulator, which we took a ton of inspiration from in designing our engine. In fact, the very, very first 2D proto version of Brax was heavily inspired by difftaichi. And you're free to look at this chart and then reasonably ask, why make another one? Well, for our own purposes, it wasn't really that we actually needed differentiability. It was more that we found the impedance mismatch between any existing physics engine and modern RL to be too inefficient for our particular product needs. But when one builds on top of JAX, one kind of automatically inherits a lot of the wonderful things about JAX, like Bedrock's primitives for vectorization, device parallelism, and of course, differentiability. So note that we're also exploring some new features in Brax that will actually make this contact physics a bit more exciting. We're also exploring reduced states for how the joints work, if you're familiar with the lingo of physics engines. So this is coming to a Brax near you soon. All right. So how does Brax actually work? I'm going to be pretty high level here, but this is all the ingredients that let our little ant here tumble rightwards forever. So we have actuator forces that torque rigid bodies around joints. This is what people like actually use when you want your creature to do something. You have to tell it how to move its limbs. We have joint forces, which limit the degrees of freedom between two rigid bodies. We have contact forces, which try to keep rigid bodies from penetrating walls or each other. And all of these forces are separately calculated and then applied to the fundamental state data, which we call QP. And this QP holds positions, quaternions, velocities, and angular velocities of all of the different bodies in the scene. And that's really the only dynamic information. So it's sort of QPs in, QPs out for this physics step function. And then looking at the pseudocode for this physics step here, we see this integrator updates the state data, and then we calculate impulses for the actuators, joints, and contacts, and then we complete the integration step. And then this is kind of a split step for technical reasons. And then simulation really is just doing this over and over and over for hundreds of steps or something. And that's about all the detail I was going to go into. This really is about as complicated as it is. And if you want to see the physics step in more detail, I encourage you to check out the repo. Alrighty. But how does it scale? So first of a handful of plots. On the left, we have the training steps per second of Brax on a 4x2 TPU v3 versus the different environments in the initial release. One major takeaway here is that we can pretty comfortably scale up to thousands of parallel environments before we start seeing diminishing returns on the accelerator. So this is this is about 1,000, 10,000, 100,000, somewhere in the 10,000 range. You start seeing this kind of elbow of diminishing returns. And then on the right-hand side, we have the training steps per second on the ant environment, which is kind of our workhorse, not too simple, not too complicated, typical case for several different accelerators as a function of number of vectorized environments. So now the x-axis is still number of parallel environments, y-axis is still number of steps, but now the colors are like a P100 GPU, a V100 GPU, several different topologies of TPU. And this is not really too surprising here. I'm just showing kind of how different accelerators saturate. So GPUs typically saturate earlier because they're and slightly slower just because they don't quite have the raw horsepower of TPUs, especially when you're stacking a bunch of TPUs. This is like 8x8. This is like 64 TPU chips. So it's like kind of an insane number of TPUs. But it's a fun plot to see because it's like, yeah, just number keeps going up. So that's nice. Now for my favorite plot, this is the reward on the ant task versus training time on several different accelerators. Every curve that says Brax is using our version of the ant environment, and the blue curve is using OpenAI's like Majoko gem ant environment. And the first major takeaway here is that training OpenAI's Majoko ant the standard way is fairly slow, but I think people in the community were kind of used to this, kind of expecting about an hour plus or multiple hours before getting a reasonable locomotion policy. But the second major takeaway here is that Brax is really fast. So we can get ant policies, as you saw, in tens of seconds. It's actually a little bit slower than it needs to be on this kind of public collab. There's some network interconnect that adds about a minute that doesn't even need to be there. So like when I'm training policies on my like production machine, everything's about a minute faster for me. But this is very nice. Very nice to have training turnaround time in minutes for locomotion policies. You might worry that our version of Brax is like much easier than OpenAI's or something for some nefarious reason. Here I have training curves for like one fixed set of Acme PPO hyperparameters. So this is like a completely different PPO implementation. It's not ours. All I've done is I'm kind of comparing apples to apples here, where I'm training a policy for the Majoko ant environment, and then I'm also training it for the Brax ant environment, not making use of any of Brax's like vectorization or anything, just like trying to see, you know, what does the exact same training algorithm do for these two things if we just switch out the step function. And here it's clear that, like, you know, these training curves are almost on top of each other. Like, it's not like our version is like way easier to learn than Mojoko's. It's just ours really does go a lot faster. All right. So up until this point, I've only really talked about how Brax is really great for running large parallel simulation on accelerators. But Brax is in JAX, and we were a little careful how we wrote our physics primitives, so it's also differentiable. And it turns out that even when you can differentiate through trajectories, those derivatives can be pretty noisy, which I'll talk about a bit more in a second. So these plots concern a really simple Reacher-like task where you can show a pretty clear win in sample efficiency. And to be clear, this isn't even the Reacher that's people are familiar with. This is like a Reacher where you give it an angle and then it just moves towards that angle with kind of like a PD controller, if you know what that is. It's like the simplest possible task one can imagine, where it just needs to go to some angle. It's very, very simple optimization problem.
Sorry, so is it chasing the laser pointer?
Yeah, it's the red here, the like little red dot is what it needs to actuate to. So like it gets a reward for putting the tip of its little Reacher arm on that dot. Does that make sense?
Yep, that makes sense. Thank you.
Cool. All right, so both of these plots are the same data, but with slightly different x-axes. On the left, we have reward on this Reacher task versus wall clock training time for PPO. And then also for a simple gradient-based algorithm called analytical policy gradients, which is literally just backpropagation through the task reward. And on the left, we see both of these algorithms solve the task in about the same amount of wall clock time, though PPO is a bit faster, like a tiny bit faster, and a lot lower variance. On the right, however, I'm plotting the performance on this task versus the number of frames of experience used. So this is like actual Reacher environment seen, steps of Reacher environment seen by the algorithm. And here, this APG clearly dominates PPO. It's about an order of magnitude more sample efficient. And that makes sense because when you're estimating a gradient via the policy gradient algorithm, that's manifestly less efficient than just using the gradient, because if you just have the gradient, you don't have to estimate it. Or is it? You might rightly ask, Daniel, you have this differentiable simulator. Why are you only showing me a gradient-based algorithm for the simplest possible environment? Why don't you just directly optimize, say, an ant policy, you know, with the gradients that you have? So quick little sidebar here for analytical policy gradients for ant. So just to be like extremely clear about what's going on here, we have some reward function. This reward function is a function of the state and the state of the ant at each time step and the action taken by the ant. The state of the system is controlled by a deterministic transition function, T, where this transition function is also deterministic, and it's a function of the state of the system and the action taken by the ant. So calling this transition function, this is just like the physics step. You know, given the state, given an action, brings you to the next state. And then finally, this pi, which is a function of the state of the system and the control parameters theta, is also deterministic. So we have all these deterministic functions. The full reward of the problem is the little r reward at each step. Because all of these things are deterministic, one can just do gradient ascent on theta to find the best reward, because this is just a fully deterministic function, and you can use JAX to take gradients with respect to theta. So why don't we just do this? We take ant, we write down this reward function, we use JAX to take the gradient. Here's what happens. So here's a training curve for ant as a function of number of like gradient updates, and you can see that it is not doing anything. This is our little ant wiggling around. I don't know what he wants. He kind of is going forward, kind of going backwards, kind of wiggling. And the reward curve is clearly not doing anything that makes any sense. It's not going up really. It's not even really going down. It's just kind of going up and down. And that's no good. So what's going on here? Why can't we just take this fully differentiable problem and take the gradient, because we have it, and use it in a way that's useful? So here's a little hint of the intuition for what's going on here. I have, just to kind of explain this confusing cartoon, I have a ball, and I'm taking this ball, and I'm shooting it at some initial direction theta. And this theta is the x-axis on this confusing plot over here. And then the y coordinate on this plot is the position of the ball after some amount of time, where the amount of time is kind of increasing. So, you know, one relevant data point on this plot is this very middle value. That's when this angle, so that's when this angle is like, you know, exactly horizontal, and it's just this is just showing the ball bouncing back and forth across the wall. And then if you look at a slightly different angle, slightly different launch angle, like, you know, a few radians, that means the ball is just kind of bouncing back and forth along the wall. So the structure of this plot is clearly getting more complicated in time, right? It's getting a little bit more jagged, but, you know, at any given moment, there's still a gradient that you can follow. Like this is a you know, there's like a finite set of points that are maybe a little bit problematic, but whatever. Like this is a function that is differentiable, and it's getting a little bit more complicated as a function of time, but it's not too bad. All right, let's see what happens when we add one extra ball to the problem. So we're adding I literally put another ball that's initially stationary, and then I shoot this guy. And then as a function of theta, I see what happens. And you can see that the distribution of the ball position gets extremely messy as a function of time. And it's actually exponentially noisy, to the point that calculating a gradient of this function after 10 seconds of simulation results in this messy, spiky object, which is essentially completely non-informative of anything about your problem. Like, you could zoom in a bunch, maybe, and take like really tiny time steps and get good gradient information, but it's like, this is terrible. This is not a function you would ever want to try to differentiate and use, because it's an enormous mess. So this, just to kind of illustrate that this isn't unique to contact physics, here's an example of a little toy called a magnetic pendulum, where you drop a magnet and it wiggles around for a while and eventually settles into some basin. Here's a more complicated version of a magnetic pendulum in action, where these are all like magnets on the bottom of this thing, and this also has a magnet, and it's just bouncing around. So the right here is actually a phase space plot showing a 5 magnet version. So imagine this toy on the left, but there's like only 5 magnets. And it's showing, based on like where you drop the pendulum, where does it end up? Where one of these basins is like one of the magnets. So it can probably, hopefully it is clear that where you drop the magnet is it's like which basin you end up in is an extremely sensitive function of where you start by like letting go of the pendulum bob. So yeah, this is sort of just, physics is really chaotic in one picture. And these kind of simple systems are actually in some sense simpler than the dynamics at play with our ant model. So with all that said, there actually is a bit of a longer story about this, but long story short, you can get around a lot of this difficulty by using an optimization technique called truncated backpropagation through time. But the gradients of systems that have contacts are just exceptionally poorly behaved. We explore this in a lot more detail in a bunch of other systems as well in our recent preprint called Gradients Are Not All You Need, which is at archive at this link. And really, this technique is kind of, the long and short of it is, you just kind of introduce, let me go back a couple slides. You just kind of add stop gradients periodically to this reward function, so that you only are ever taking gradients through like 10 steps or so instead of like 1,000 steps, which is the baseline environment. And that greatly stabilizes optimization, but it's extremely sensitive to a lot of things. So this plot here is showing the like reward on this locomotion task as a function of just that one parameter, truncation length, and then different colors or different learning rates. And here you can see, like, yeah, we got an ant that can locomote, but it's, you know, it's like okay, and it also took like way longer, and it still kind of flips over on its head at the end, because it's just not as good as PPO. PPO is, in defense of APG, perhaps we spent way longer optimizing our version of PPO than we have gradient-based algorithms, but really, in my experience, it's been just so much easier to learn locomotion policies with these more model-free like methods like SAC or PPO or even ES. They all work very well. They're all very good at estimating gradients, and it just seems using the raw gradients is always a little bit difficult. Okay, and then kind of zooming back now. Finally, just some simple engine comparisons. I have the performance of Brax plotted against several other engines on these astronaut benchmarks. These were introduced by some of the Majoko authors. The left two plots here are showing like linear and angular momentum non-conservation as a function of simulator fidelity, and the rightmost plot is showing energy non-conservation. So these are kind of confusing plots. The way to read this is up and to the right is better. And the major takeaway is that Brax isn't really like overwhelmingly better or worse on any of these things, although we're actually pretty good at angular momentum conservation. But Majoko Rungakuta, which is one of their fancy integrators, is like really good for energy non-conservation, but we're kind of middle of the pack for angular momentum and energy. So this is just you aren't sacrificing much by using Brax. It's kind of, I mean, it's sort of unsurprising. All these engines are using very similar things under the hood. They're just kind of differences in detail that cause these sorts of numerical inaccuracies to be slightly different. All right, so this kind of the story so far. We've enabled this really fast training of this collection of familiar 3D rigid body physics-based RL problems by making liberal use of JAX's compilation, parallelization, and vectorization primitives, JIT, PMAP, and VMAP. We have a bunch of really nice collabs to make jumping in and using Brax super easy. You too can train Ant in about a minute with PPO. And we're adding new environments pretty regularly. So since we've submitted to NeurIPS, we've actually added like Reacher, UR5E, Hopper, Walker 2D, Inverted Pendulum, Swimmer. There's always more things getting cooked up because there's just infinite RL environments that people care about. And if you have a favorite environment, please let us know. We'd like to try it out, and we do accept pull requests. There's actually one happening right now, which we're about to add a new environment to Brax. So for some next steps, we're improving the contact physics. We want to add more primitives, so more types of colliders, joints, actuators, integrators, better stepping schemes. So I actually have a branch where I'm working on slightly more general constraint physics for like position-based dynamics or velocity level constraints, if you know the lingo. And we also are working on reduced coordinates. I mentioned this earlier, where right now everything in Brax happens with maximal coordinates. And a lot of the other more popular engines are switching or have already switched to reduced coordinates, which is a bit more technically demanding on the programming side, but does have very nice stability properties and sort of uses fewer degrees of freedom to simulate the system in a very precise technical sense. And then finally, we'd like to do more differentiability. So there's actually a bunch of tricks one can play with contact physics when you have differentiability that I haven't talked about at all. And then I'd like to think even more about this back propagation through time, this BPTT algorithm that I was talking about for the gradients with Ant. Differentiating through trajectories is still really hard, and there's a whole bag of tricks that one can apply to this problem, like shadowing methods. There's tons of stuff left to do to make the gradients in Brax better. So that's really all I had slides-wise. Happy to talk more, answer any questions. We can jump back over to our or our humanoid policy over here. Let me see if it's done training. Yeah,
it's fascinating how fast they train now. Like honestly, I'm a total RL noob. I just fork repositories and run stuff. But the first time I tried it, it would take I remember days on a CPU just to make things work.
Yeah, that was unacceptable to us. So we really wanted to. Here's our Ant, or here's our humanoid now. And this took, let's see, this took about 5 minutes total. So about 2 minutes to compile and 3 minutes to train. So yeah.
I mean, he looks happy.
Yeah, he looks happy. I mean, it's it could be more symmetric and maybe a bit less wobbly. This is actually a lot of the things I'm working on right now are making it so he's less kind of wiggly. Well, you can kind of watch him in slow motion here. Like, look at these joints. These joints are like way too wiggly, but that's okay. He's still running. I think maybe the biggest surprise to all of this is that people spent a really long time trying to get like exceptionally high quality physics in their simulators, And it turns out that the underlying reinforcement learning problem actually isn't really any easier or harder when your physics is like a little bit lower quality. It's kind of just the same, and you can do lower quality physics way faster, which is evidenced by Brax. You can also do a really good quality physics this fast. You just have to be more careful, which is kind of what's coming soon in our future versions of Brax. But this was definitely kind of a $20 bill laying on the ground in terms of being able to prototype things that people were familiar with much, much faster.
That makes sense. Christian says in the chat he has a few questions. So while I wait for him to type that, you had shown a slide where you demonstrated how this scales across TPUs.
Mhm.
In what use cases is it really helpful to scale across such a huge number? And is there like any special tricks that go into making it so scalable, or is that just the JAX framework underlying?
So to the first question, essentially you want that many TPUs when you're, well, okay, it kind of depends. Like if you want something to happen quickly, then you need to be able to get lots of frames of experience. And for the sorts of reward functions that we have included in like Brax today, you don't need like, an 8x8 sliced for that. All these reward functions are pretty straightforward. They're like, go to a target, locomote in some direction. For something that would like actually require many TPUs, that'd be more like coordinated gameplay, something where like you actually the underlying reinforcement learning policy that you need to learn takes just gazillions of frames of experience before you can start estimating really good gradients. So yeah, it's sort of like a different grain size of problem you need when
Makes sense.
and even then, like you don't need an 8x8 slice. That's just if you want it to go fast, which everyone wants things to go fast. As for how it actually does it under the hood, it is a combination. I mean, it is JAX. It's short answer JAX. We write everything to be branchless so that we can make use of the vectorization primitives, and then kind of once you have things vectorizable in JAX, it's almost just as easy to make them parallel across machines. And then TPUs are sort of magical in their ability to just scale that way. Like you can also do this on on GPUs. I've run JAX, or I've run Brax on like 8 GPU machines, and that works. Like you don't have to do anything special. You connect 8 GPUs and run it, and it's fine. I haven't actually tried a cross machine parallelism in Brax yet for GPU. For GPU, it's straightforward because TPUs kind of do that for you. But I suspect it would work.
Yeah, I guess as you scale, it starts to differentiate. TPUs start to outperform for the initial bits where you have just 8 GPUs and just one 8x8 chip. I think it might not be that different.
Yeah.
Awesome. Thanks for answering that. Christian has typed in his questions, so I'll highlight them.
Great.
Are there restrictions that come with making a simulator purely jittable or differentiable? Example, how do you kill or delete an agent, or body given shapes must be static?
Yeah. So this is a whole thing. Yeah. So right now, the restrictions are kind of what you might expect. So like if you want there to be dynamism in the scene, you have to do a lot of that management yourself, like, and sort of already have those objects sitting around. So like, say you want an ant to interact with like a variable number of balls in a scene. For JAX and for like compiled JAX, the staticness of this kind of demands that you already have those 3 balls, or as many balls as you expect the ant to ever interact with, defined in your proto, and then you have to kind of manage that yourself. So you would have to like move the balls in and out of the scene as they need to be used by the ant. So that is sort of like, gesturing at a missing interface between Brax as it exists today and something like, Unity or Unreal Engine, which handles like the way you interact with kind of fully fledged game engines obscures a lot of this memory management. It's just like, you put a thing in the scene and you kind of spawn it dynamically as you need it. Whereas doing things in JAX really does necessitate that everything be statically compiled, and you can't really have these like dynamic shapes anywhere. The getting everything to be vectorized, I mentioned before, requires things to be branchless, which is something of, I mean, it's not the end of the world. It's pretty straightforward to take modern like physics pipelines and turn them and make them branchless. The tricky bits come for actually making modern collision culling algorithms branchless, and that's actually a very tricky problem. Not just branchless, but like branchless and efficient on TPU architectures. So like we have some somewhat clever culling algorithms that work great on GPU, but if you try to run, say, like 10,000 objects interacting with each other on a TPU, it chokes pretty poorly. Like that doesn't work. Like it has to do with the memory architecture of TPUs and how they are kind of bad at doing random access. Yeah, they're just bad at that, period. Whereas GPUs are a lot better at that.
Sorry, in what case would it make sense to like spawn so many agents?
I mean, if you want to do something like, like a capture the flag game, say you have like 10 ants that are trying to capture the other 10 ants flag. That's like a lot of objects that can collide with each other in principle, and you can't do things like dynamically turn colliders on and off like you could in another game engine. You kind of have to statically have all of the things that are going to interact up front. So you have to be a bit clever about how you do culling and how you lay things out.
Okay. Thanks for clarifying. Christian has another question. What challenges come along with creating a simulator in a functional framework? How do you handle state?
Yeah. So yeah, like short answer is we have to be fairly careful. Where the things that we expose is like the QP data. That's the only dynamic state of the problem, and that's what's passed around functionally. Where like you start. In fact, I can show this. Let me jump back over to my slide or my Collab here. What's the best place to do this? I can do it down here where we do this rollout. Add a bunch of cells here. So you see this loop here, which just generated this trajectory, is really just driven entirely by these two lines, where we're getting some action on the environment, where this is like the policy. This is the function, the inference function. This inference function is taking params, which is like literally NumPy weights of a neural network. We're giving it the observation for the system and some randomness, and that's producing an action. And then this is the Brax system step, and all we're giving it is the state of the system and the action. So we can look at the state data. The state data has a bunch of stuff in it for kind of bookkeeping, but really state.qp is the state data for the system. So this is like the positions of all of the body parts, the quaternions for all of the body parts, the velocities of all the body parts, and it's the 0 is the 0th one, so it's not moving yet, and ang is just angular velocity. So like we've written it functionally so that we only really pass around the data that needs to be passed around, and this is like the minimal state data for the problem. The system specification has a bunch of other stuff that's statically compiled. So for example, what am I calling? Is it just env that step? So yeah, env fig has all of the stuff that's kind of compiled away, which is things like where colliders are attached, how big they are, what the friction is, the inertias, the masses, and then for joints, it's things like where are for a joint between two bodies. So this is like the right knee, which is connecting the right thigh and the right shin. It's like, how are they oriented with respect to each other? How are they rotated? What's their damping? What are their angular limits? All this stuff is statically compiled, and it's essentially read in at initialization and set for the rest of the simulation. So that does mean if you want to change this stuff, then that's a little annoying, but it's possible. It's just like when you're going to be simulating a humanoid and none of this stuff is changing, then by construction you want to have this stuff statically compiled.
I'm waiting for a response from Christian, but that'll take a second. This made sense to me.
Cool. Yeah.
Awesome. I'm just checking if there are any other questions. I don't see any. I think Christian will have a follow up. In the meantime, for anyone who's like me who fairly knows his way around jargon in RL and is quite new to it, do you still recommend to play around with Brax or any other learning resources that you could suggest?
Yeah. So I mean, there's using Brax is definitely like I would suggest checking out like the sort of standard Jax resources first, because it's it's built on top of Jax and it has all of the sharp edges that Jax has. Probably the best entry point for folks that are maybe not as well versed in reinforcement learning is our basics collab, and I can actually let me see if I can jump into that really quick. I can show that off. I'm just changing the URL here to basics. Don't bolt anything. Moment. So this basics collab really just steps very, very simply through like a simple configuration with like a bouncy ball, showing this bouncy ball bounce. You can kind of play with the system parameters for this bouncy ball, and it shows you how to like construct the system. Also like how to define joints. So here's like a two pendulum system where you can watch it like swing, and how to like actuate it to some target angle. So like this is really the simplest interface to Brax physics internals. For reinforcement learning material, oh geez, there's a gazillion reinforcement learning tutorials on the internet. I think I learned RL probably. I mean, I would suggest anyone that is super interested in RL, check out OpenAI's intro materials. They have like a getting started ramp up set of articles and like blog posts about doing stuff like just kind of getting up to speed in RL. And then I would also suggest anyone that is really serious about RL, just try re-implementing the policy gradient algorithm. It's kind of one of the workhorse algorithms in RL, and it's a good experience for like really grokking what is going on in these sort of gradient estimator approaches, because all these RL algorithms are really doing some kind of fancy gradient estimation.
Thanks for answering that. Amit asks, how do you compare Brax to Chim?
So we do a couple of comparisons in our paper. Probably the most relevant one for folks is just like learning curves as a function of number of environment steps seen on the same, using the same algorithm. So like literally take some reference implementation of PPO and then use the Brax gem end of step or use the Majoko gem end of step, and then just see what happens. And we showed that, you get basically the same training curves for like ant, for the same thing for humanoid. Half cheetah they're not quite the same. There's some subtleties in contact physics and 2D that kind of make things not quite the same. Short answer. But I mean, the kind of higher level point is that they're not the same. So like, I will be the first to tell you that, hopefully not the first to tell you that Brax does not do physics the same way Majoko does. Like, sure, in the limit of like very, very, very tiny step sizes. I mean, even then there's some subtleties around contact about how they treat things differently, but like they're different. Like there are physics differences. There are important physics differences between Majoko and Brax, because Majoko's been around for like over a decade at this point and has all kinds of fun features that make it very good at doing physics. That said, you can get pretty close with Brax. Like the places where we're missing are things like some subtleties during contact, some subtleties around joint physics. So you probably saw the joints were a little bit slidey in Brax. That can actually be shored up in Brax by turning up joint stiffnesses a bunch, like just making them like what you really want to do when you're modeling a joint is to say like this joint is infinitely stiff, because that's sort of how robot joints are. I mean, it's not, like technically there's some extremely tight spring constant that's controlled by like electrostatics and atoms and metals that are extremely like, tens of thousands of newtons per meter or something, or like millions of newtons per meter. But sure, zooming out, that joint should be like infinitely stiff, and there are methods of doing this. So, for example, the Featherstone algorithm is what Mujoko uses to model infinitely stiff joints. I have a branch where I'm working on using position-based dynamics to model infinitely stiff joints. And even Brax today, you could get close to this by just cranking up the springs and lowering your time steps until it was good enough for your purposes.
That makes sense. Just as a reminder to people, if you signed up on this link, we'll send out all of these links, the paper that Daniel just referred to, and the link to the repository, the intro collabs. You'll get an email. You don't have to complain in the comments and make my colleagues unhappy and ask them to make me answer that. Everyone understands it's a pain for me. Please don't do that. Wait for the email. Here's a question by Christian. Is there a Unity-like editor to create scenes, or can you import them from other frameworks into Brax?
Not yet. So we actually did some Unity integration, months ago, just to kind of prove that we could, but then it sort of became sidelined as we were doing other things. Right now, the best way to do like interactive system hacking is we've actually made the Collab pipeline fairly quick, where like if you edit in text a system config and just like hit enter, it'll visualize within a second or so. So that is the current supported way of doing system editing, but it is on our to-do list, fairly high priority to get some interactive tooling in, because I don't worry, I understand how irritating it can be to only interact with these heavily visual scenes through pure code, because people are used to their fancy editors where you can like click and drag the sphere and move the sphere and rotate the stretch and squash. Like people are rightfully spoiled by things like Unity. Unity makes your life so nice. It's such a delightful experience to just kind of put together a scene graphically.
Have you seen this channel called Mix and Jam on YouTube?
No, what is this?
They try to, side note, totally different tangent. They try to recreate game dynamics in Unity. It's like fascinating stuff.
Oh,
to see that
interesting.
you can do all of this in the game. In the engine.
Yeah. That's sweet.
Awesome. Thanks for answering that question. I'll give Christian a few more minutes. If he has any more questions, usually I trust him to ask all the smart questions. I ask the dumb questions. In in the meantime, where can the audience find you on the internet apart from the repositories?
Yeah, so I'm on the repositories. I'm on Twitter at Bucket of Kets.
That's why I couldn't find you.
Yeah, I actually don't super advertise. It's not like I'm trying to be anonymous, because I post my papers and stuff all the time there, but it's more just like having one layer of anonymity makes it slightly less annoying. I don't know, because I don't always post about work stuff. It's sort of my somewhat pseudonymous. I mean, not anymore. I'm going to be posting this on YouTube. It's not anonymous. I'm friends with all of the people. Post me when they're posting their papers. I'm on Bucket of Cats on Twitter.
Okay, awesome. Again, you'll find that in the email that goes out. Find Daniel also in the repository.
I did see you used my my LinkedIn headshot for this picture, which was pretty funny, because that picture is from 2012 when I was in. That was like the very first office I was in at Berkeley in grad school. It was a very beautiful office, and we eventually got kicked out of it. But I don't know, that picture brought back memories. Haven't seen that face in a while.
We were trying really hard to find you on Twitter, and we couldn't. Now we know why.
Yeah, that means I was successful in being slightly pseudonymous.
Awesome. I don't see any questions from Christian, so I'll wrap up here. Thanks again, Daniel, for joining us. People, please check out the Brax repository. Sign up on this link to receive these as email updates. And I wanted to point out another repository developed by a Kaggle Grandmaster. It's called Jackson. This is more introductory levels stuff for people like me. Let me share my screen in a second. Screen. It's always tricky to pick the right app. But I quickly wanted to mention this. It's a set of 100 jacks exercises developed by Rohan Rao, who's a 4x Kaggle grandmaster. So he's a grandmaster in all categories. For Kagglers, they know how hard this is to achieve. It's a set of 100 exercises designed in a way to actually make you learn jack. So it's not a test, it's more of a learning experience. I'd highly encourage everyone to check this out. Just wanted to mention this repository to everyone.
Yeah, that's sweet.
And thanks again, Daniel, for joining us. Christian says thanks. Sorry, Christian, you couldn't join us. Hopefully, you'll join us in the future session. And thanks everyone for your time.
Yeah, thanks for having me. Thanks, y'all.